Hello, my name is Dylan Kruep. I am part of the Department of Mechanical and Nuclear Engineering at Kansas State University. My advisor is Dr. Gurpreet Singh, and I'll be talking about the mechanical property assessment of silicon carbide fiber reinforced epoxy-matrix composites today. General overview, we'll talk about the application of these fibers, as well as the objective of our project, the materials used throughout the project, the procedures and standards used, as well as the tensile testing data acquired, and then our future work and conclusions. So to begin with applications and relevance, these fibers are incredibly applicable in industries such as aerospace, the nuclear industry, and energy industries in the forms of thruster nozzles, hypersonic vehicle reentry, thruster nozzles we can see here, aero engine vanes, as well as in gas turbine engines for the energy industry. We can see here actually, again, also applying to aerospace, the GE jetliner engine with parts made of silicon carbide fibers, the combustor, the shroud, the blade, the nozzle, as well as nuclear fusion reactors with components such as first wall of cladding, flow channel inserts, control rods, and diverters. Now, the reason these are so important is because they have high thermostructural applications, meaning they can retain high strengths at ultra high temperatures, much like comparable metals. However, they are much less dense and thus weigh a lot less. Because of this, a lot of instances, you're seeing a great increase in efficiency, as well as with a great increase in efficiency, less fuel being burned and less money being spent on fuel. So additionally, the silicon carbide market is projected to grow based on this market projection from 2019. So we can move on from here to talk about our project. So our project was to determine the mechanical properties at room temperature of 3 different commercial silicon carbide ceramic fibers when used to reinforce composites using a polymer matrix. So we accomplished this by comparing the Hi-Nicalon type S ceramic and Tyrano SA3 fibers. We made 3 composites of each of these fibers, using each of these fibers as reinforcement before tensile testing them to get the elastic moduli and the tensile strengths. So here we can kind of just get a general feel of what these look like as far as on their toe bundles on a spool. We did some scanning electron microscopy in order to get a general feel of what the size of these are, general feel and scale, as well as we wanted to see what the distribution of diameters of individual fibers throughout an entire bundle was. So we can see that here, where we have a general distribution for this Hi-Nicalon type S fibers with an average diameter of 13.3 microns, as well as on the ceramic, we have a general average of 11.2 microns, and the Tyrano SA3, 11.3 microns for their diameter. And we can see how this compares to the manufacturer's data by looking here. Our Hi-Nicalon type S average and our Tyrano SA3 average are actually 1.3 microns above what the manufacturer suggests is their fiber diameter. However, the ceramic fits right in the range provided by ceramics manufacturers. So that's kind of nice. Additionally, we performed Raman Spectroscopy in order to see the ratios of disordered to graphitic carbon, or disordered to ordered carbons throughout each fiber. So you can see here the ceramic, the Hi-Nicalon type S, and then the Tyrano SA3. The ceramic had a practically 1-to-1 ratio of disordered carbons to ordered carbons, and the Tyrano SA3 1.15. However, the Hi-Nicalon type S with 1.5 has a great deal of free carbons. I believe this has something to do with the, based on literature, something to do with the fabrication methods used for this for this Hi-Nicalon as opposed to the ceramic and Tyrano, or the Hi-Nicalon uses electron irradiation during their fabrication, and one of their the properties they've tried to keep in mind when producing those is keeping up the free carbon. We can also see from this graph the kind of the similarities between all of these, because it kind of highlights, everybody has a G prime peak, everybody has a G peak, everybody has a D peak. However, ceramic, despite all of these being silicon carbide fibers, has a higher silicon peak and silicon carbide peak, which is interesting. So we also, to perform our project, we had different reinforcement methods. We used chopped fiber filler and continuous fibers. To do this, our chopped fibers, we used 1 millimeter lengths that we then mixed into our epoxy resin. And with the continuous fibers, we cut off 2-inch fiber bundles and place those along the gauge lengths of our molds before casting the resin in our mold. Here we can see the shape of our dog bone standards, our tensile test specimens. We use this type 5 ASTM D638 standard. Here are the dimensions for that here. And that's just to make sure that we had consistent specimens throughout. Here's the procedure for the chopped fibers. We can see that we chop these fibers to 1 millimeter lengths before rinsing them with 2 milliliters of isopropanol before sonicating in a box sonicator for 30 minutes. We then mix this in with our 3-to-1 epoxy hardener with epoxy resin, and then mix the fibers in with that to get a 0.60 milligram per milliliter concentration, and then pour that mixture into the molds and set and cure these for 20 to 22 hours before tensile testing. So here's what those kind of look like. You can kind of see here generally what some fibers along that gauge length for the Hi-Nicalon as well as the ceramic. It's not quite as obvious in the Tirano. I believe there's one right there you can kind of see, but this picture is just not very clear. So I apologize for that. So we tensile tested those, and this is the data we've acquired from that. As you can see, the ceramic performed very well with a 1.45 gigapascal elastic modulus, followed closely behind by the Tirano SA3 composites, and then the Hi-Nicalon Type S composite. The Hi-Nicalon actually did not perform very well. It did not show much improvement to the neat epoxy at all, which leads me to believe that there might be some sort of inconsistency with this test. So we'd like to perform some more tests in order to see what we're kind of, if that is consistent as far as the comparison goes. So we moved on to continuous fiber testing, which had fewer steps and less opportunities for inconsistencies during testing. So we chopped the fiber bundles to 2-inch lengths before mixing, and we mixed our epoxy resin and then placed the fibers along the gauge length before pouring that resin and setting and curing, and then tensile testing again. So here we can see what those composites look like post-curing, and we can see they each had roughly 0.5% volume fraction for each composite. So using that, we were actually able to calculate a theoretical modulus to go along with our tensile data, or a theoretical longitudinal elastic modulus, as well as a theoretical maximum tensile strength. But here we can see the experimental data, where we had 3.47 for our elastic modulus for, on average, Hi-Nicalon Type S, and then followed behind by the ceramic at 3.14 and the Tirano SA3 at 2.95. However, the fracture strength maximum that we calculated for a theoretical value is slightly lower than our experimental value for the Hi-Nicalon. So there are some questions to be had there, as well as the ceramic elastic modulus is slightly higher than the theoretical maximum. So because of this, we went ahead and we tested some more, 3 of each of these composites in order to see how those might compare and see if there was just some sort of inconsistency in our testing and performance. But as you might be able to tell, those were fairly consistent and actually maintained above those theoretical maximums. But here, the Tirano SA3 actually peaked above the ceramic as far as elastic modulus and tensile strength is concerned, sitting at 3.49 gigapascal, 3.09, and 3.01 of Hi-Nicalon, Tirano, and ceramic, respectively. But each of these is still showing significant improvement when compared to this, just a plain neat epoxy tensile test specimen. One of our graduate students, Shakir bin Majib, has also performed some fiber bundle testing following a procedure described in literature. Here we can see some Hi-Nicalon, Tirano, and ceramic samples. They get pulled by the tensile tester here, and we got some data from that. So here we can see that data. The Hi-Nicalon Type S showing 72.54 gigapascal, followed by the Tirano SA3 and the ceramic. However, the ceramic and Tirano bundles did not fracture entirely across their bundles. So I'm not entirely sure that this is a true comparison, or that a true comparison can be made from this, but it is worth looking at and considering anyway. We also performed some initial testing with 3D printing, where we tried to chop up the silicon carbide fibers in 0.60 milligram per milliliter concentrations and distribute them throughout a photopolymer matrix before 3D printing composites. but we'd like to continue working on that and get some more consistent procedure and data going. But this is kind of our initial, what our initial experiments show. From that, we can see the Hi-Nicalon type S followed by the Tyrano SA3, and then finally the ceramic composite as far as the order, which follows along with what our continuous fiber epoxy resin composites were showing. So to conclude, our chopped fiber composites seem to imply that ceramic and Tyrano SA3 fibers show significant improvement on the neat matrix. However, this is contradictory to our other tests that we performed, such as the continuous fiber composites, where they showed Hi-Nicalon type S providing the highest improvement of strength and modulus of the 3 fiber types, followed closely behind by the Tyrano SA3 and ceramic respectively. And this data is supported by the manufacturer's data for the silicon carbide fibers and our other testing through other methods. Further testing of the variables we'd like to conduct would be involving how they might affect the modulus of strength, such as exposing the fibers to temperatures above 1000 degrees Celsius before reusing them as a reinforcement, as well as the ideal concentration and length of chopped fibers in a polymer matrix. We're also going to be performing future work using silicon carbide fibers as a filler for a silicon carbide photoreactive polymer precursor matrix in order to 3D print a 6-6 ceramic matrix composite and see how well that works. I'd like to acknowledge our financial support from the National Science Foundation, as well as PIRE, as well as additional thanks to Dr. Sara from Spirit Aerosystems and Ali Badran and Spencer Dancero from the University of Colorado Boulder for listening to and providing feedback for my past experiments and presentations with 3D printing with these silicon carbide fibers. You can contact me at dmkruep@ksu.edu or Dr. Singh at gurpreet@ksu.edu, listed here. Here are some references for you. And without much else, thank you very much and have a great day.